To find the area between two curves, again, we have to identify the function that has the greater function values. So we list that function, or the greater function first, whichever function has the larger function values over our given interval. But sometimes the greater function can change. So if two functions cross over each other, the function taking on those greater values can change from one function to the other. So we need to set up a process for how we deal with situations like that. So in example 6, we want to, again, set up a definite integral that represents our shaded region. So when we look at this first shaded region, we can see that our function g of x is taking on the larger function values. And then when we get into the second shaded region, our function f of x is taking on the larger function values. And what happens is right at x equals 5 in this case, we get that change from where one function is taking on the larger values to where that switches to be the other function. So in this case, what we'll do is set up two separate integrals. The first will evaluate from 0 to 5. On that interval from 0 to 5, g of x is taking on the larger function values. So we would write this as g of x minus f of x dx. And then we would add the second interval, the second shaded region, which in this case is the interval from 5 to 10. Now on this interval, f of x is taking on the larger function values, so our integral statement would be f of x minus g of x dx. So in cases where our functions cross over with each other, we take that integral, split it up into two, possibly three or more different integral statements, looking at where that crossover point occurs. So in example 7, we want to find the area bounded by these two graphs on the interval from -3 to 1. So the first thing we need to identify is which function is taking on the larger values on which interval. So we're looking at -5x and y equals 0. We'll set our window to be an x-min of -3, an x-max of 1, and then we'll use that zoom feature to automatically adjust the y-axis. So 10th option down, zoom fit. So from -3 to 1, we have the x-axis, or that line y equals 0, and then we have our line -5x. So on the interval from -3 to 0, -5x is taking on the larger function values, and then at 0, they cross. From 0 to 1, our line -5x has smaller function values than the x-axis. So we would write this as two separate integral statements. The first from -3 to 0, where we would integrate -5x, since on that first interval, it's again taking on those larger function values, minus 0 dx, and then plus the integral from 0 to 1, where now y equals 0 takes on those larger function values, so we would integrate 0 minus -5x. So just cleaning up our integral, simplifying the two expressions a little bit. We can reduce this down to the two functions that we'll be integrating. Integrating this first function should give us a result of 45 halves. And then integrating the second function from 0 to 1 should give us a result of 5 halves, which would give us 50 over 2, or a total area of 25. Similarly, in our last example, we would want to graph these two functions and determine where that split happens, where they cross over, and which function is greater on which interval. So in this case, to solve where these two functions are equal to each other, one thing we could do is take 3x squared minus 7x and set it equal to 0. This would have worked in example 7 to find that point of intersection as well. We can take those two functions, set them equal to each other. In this case, factor out an x to get 3x minus 7 equals 0, which gives us two solutions, x equals 0 and 7/3. We're considering the interval from -2 to 2, so 7/3 would be outside that domain. So our two functions cross over at x equals 0. So our domain that we have to consider really is -2 less than or equal to x, which is less than or equal to 0, and 0 less than or equal to x, less than or equal to 2. So we have two different areas to evaluate. We could graph the functions to see which one is taking on the larger function values on each interval. And what we'd see is that on the interval from -2 to 0, 3x squared minus 7x takes on the larger function values. And then on the interval from 0 to 2, y equals 0 would take on the larger function values. So this would have us integrating from -2 to 0, the function 3x squared minus 7x dx, and then in a second integral, we'd be integrating from 0 to 2, the function -3x squared plus 7x dx. So we could evaluate both of those definite integrals, and that final result should end up being a total area of 28.